Buildings and infrastructure are a vital part of human civilization and significantly contribute to global carbon emissions. Research indicates that up to 85% of carbon emissions are from the early stage of the building's life cycle and mainly focus on raw material manufacture, while 5 to 15% CO2 will be emitted at the last stage of the building. Our method is called DCUS, decarbonization of the raw material, carbon capture from air, usage of the CO2 for material strengthening, and finally, permanent storage of the CO2.
Okay, now we are all our three together actually is the team for earth4Earth for the competition. So behind us, this is the factory. We're going to manufacture 10,000 tons. The earth bricks to absorb the 1,000 ton CO2 from the air.
This is the reactor that we will conduct our decarbonization reaction in. So to remove the CO2 from the calcium carbonate, from the limestone, we will mix it in here with the sodium hydroxide solution. The sodium hydroxide and the dissolved sodium hydroxide and calcium carbonate will react to form Portlandite or calcium hydroxide and sodium carbonate. So here we are. So you can see here is a landfill where all this soil comes from Wuhan city, for example, from projects such as building the underground. So this is the waste soil, and all this waste will be reused and have a second life in our project as carbon negative bricks. So over here we will have our mixture of sand, lime and soil. That's the mixer silos, and the material will go onto the other side where they will be compressed for brick.
Now we are looking at the carbonization of this material. If you're looking at the inside of the block, you can see that's earth materials in the main body. But the external layer, you can see it looks like very different. That's because the rammed earth absorbed carbon dioxide to form a very well and hard external surface. So now actually we are looking at the most important part of the materials. These materials absorb the CO2 from air. Because we understand once this material has been built in the buildings, they're probably hiding somewhere else. So for the bricks, generally that's the really good chance to allow each brick exposed to the air in the maximum areas. And also we can control the temperature and the moisture. So we can see, you can see this cage and this tower. Generally they have making all these bricks and can be possibly actually to absorb the CO2 as much as they can.
The thing for the negative brick, to the end of the first life of the brick, it can go back to the ground. It can be the soil as the first you hear, because when we add lime and the sand and the soil together, it's not to another like concrete. It can squeeze to the soil. When the brick absorbs carbon dioxide, it can turn to something neutral. It can go back to the ground and to grow vegetable.
Rather than just absorbing CO2, we develop negative carbon construction material as commercial products. The cost of the carbon removal will be fully paid off by selling the products to the market. The extra cost due to the introduction of the decarbonization is offset by the value increase from the material strengthening from the captured CO2. There is a large market for our products in both developing and developed countries. Repurposing excavated horizons or waste construction soil as the main raw material also provides economic benefits. Imagine if we produce 80 billion tons of rammed earth to replace the concrete with an 18% carbon capture rate. As our data shows, we can capture and store about 15 billion tons of CO2. That's equal to 50% of the world's annual carbon emission. At the same time, we will produce 35 billion tons of sodium carbonate as byproduct, which can be used as a CO2 absorber to produce sodium bicarbonate. Then, we can theoretically capture another 15 billion tons, equaling all of the world's CO2 emissions. With the application of DCUS and modernization of earth construction, we will make all buildings become CO2 absorption plants and remove gigatons of carbon dioxide from the air.